Hi, in this video, I'm going to talk to you about sampling. Specifically, this is a step that one concerns oneself with once the research design has been decided on and the research instrument has been prepared. The next question then is who to gather data from, and that's where sampling comes into being. Our focus here is going to be on sampling, specifically design, procedures, and size. We'll begin by contrasting sample and census, then going to sampling design process, a classification of sampling techniques, examining the strengths and weaknesses of techniques, and lastly, evaluating considerations of sample size. Now, a sample is a subset of a population. We frequently use or gather data from a subset of the population. But before we even examine when to use which of the two, let's consider a common belief of what a sample is and what a population is. People often believe that a sample is small and a population is large. This is partly correct. A sample is indeed always and must always be smaller than the population. But a sample doesn't have to be small in absolute terms, and a population doesn't have to be large in absolute terms. In other words, a population could involve 12 people, and a sample could be 200 million people. What is important to note here is that, yes, indeed, sample must be smaller than the population, but in terms of absolute numbers, sample and population could, be small or large in absolute terms. If one is interested in examining the characteristics of the students in a classroom, then the students in that classroom, let's say all 30 of them, are part of the population. One could draw a sample of 6 people from that classroom, and those 6 would be a sample. In this case, sample is 6, and population is 30. The question is often asked is whether I should use a sample or census. In almost all cases, the choice is to rely on a sample. Reasons for these are manifold, but let's just review a few of the considerations. When your budget is small, you want to consider using a sample because it's going to cost more money to gather data from everybody. If time available is short, again, sample is preferred. If your population size is very large, you may just not have the budget or time to gather data from everybody. In that case, again, sample becomes a logical choice. If the variance in the characteristic of interest is very small, a sample might suffice. In an extreme situation, imagine every observation unit has the same number. If that's the case, that the variance is 0, then even one observation should suffice. If the cost of sampling errors is low, sampling errors are errors attributable to drawing a sample, then again, a sample is preferred. On the other hand, if the cost of non-sampling errors is high, then you may want to consider maybe, again, if the cost of non-sampling errors is high, a sample is preferred. If the process of measurement results in loss of the observational unit, take, for example, somebody's interested in examining how long light bulbs in Home Depot last. They have 2 options. They could pick, 20 light bulbs and run them out till they burn out. In doing so, those 20 light bulbs are going to be lost. Right? On the other hand, if they were to do the same thing, checking the life of the light bulbs for the population, it would mean losing all the light bulbs in the store, which would mean there would have no light bulbs left to sell. Right? So clearly, when the observation unit is destructive, it makes sense to use a sample. Lastly, if you want to pay attention to individual cases, again, sample is the preferred option. The sampling design process involves a set of steps, defining target population, identifying a sampling frame, picking a sampling procedure, deciding on the sample size, picking sample elements, and then finally gathering data. The first step is defining the target population. This is typically informed by the problem. The problem defines or helps inform the choice of the target population. The target population is what you want to draw inferences about. That's your what you really are interested in, or is the area of interest for the researcher. This could be a individual person. It could be a family or a household. It could be people belonging to a certain, it could be a department, could be a company. So the target population may have one individual or many individuals as part of it. Furthermore, a target population may be defined more narrowly as fulfilling certain characteristics. Like a target population might have maybe defined as people driving a Tesla in the city of Boston, Massachusetts, right? So then we've kind of got like a behavioral variable here as well as geographic variable as part of our target population definition. Now, it is from the target population that one would ideally like to draw a sample. But as it turns out, you may not always be able to draw a sample from the target population. And so you might end up drawing a sample from a sampling frame. Let's understand the distinction out here. Let's assume the goal here is to study Tesla owners in Boston, Massachusetts. That's the target population. Now, ideally speaking, you could identify all these people and draw a sample from them. But let's say we have decided on using an email invitation to a web-based survey for our research instrument. This means in order to participate in the study, every respondent must have a working email address. It's not surprising. I mean, it's fair to assume that every Tesla owner would have a working email address, but would have an email address. But whether it's working or not depends. Okay? Some Tesla owners may have given an email address that is not an accurate one because they care a lot about their privacy. Others may no longer be using the email address used to when signing up for buying a Tesla. Then there might be others where emails from Tesla might be going in their spam folder. Therefore, you may have a smaller number of people who have a working email address, and that would be the sampling frame. The sampling frame would be Tesla owners in Boston, Massachusetts, with a working email address. We would then draw a sample from this sampling frame. How we draw the sample is the sampling technique. We could either use a non-probability sampling technique or a probability sampling technique. In a non-probability sampling technique, the sample is drawn using personal judgment. And for this reason, because we're using personal judgment, there's no way of estimating the probability that any population element will be included in the sample. So there's no way of ensuring the sample is representative of the population. This is not to say it is not representative. We're just saying out here, we cannot assess whether in fact the sample is representative of the population. So we have no objective way of evaluating whether the sample is adequate or not because of the nature of sampling being conducted out here. There are numerous reasons why somebody would do non-probability sampling. Right? One of them is convenience. It might just be easy to gather data from people around you. Let's say marketing researcher is interested in marketing research. Researcher is interested in gathering data on some consumer behavior of interest. Rather than doing drawing a sample from a database of all Americans, he or she might decide to gather data from students in their marketing research class. Students are indeed Americans. So one could argue, well, they fit the definition, but these students are being used, are being invited to the study because of convenience reasons, just because you have access to them. Another example would be somebody who has access to some email list, reaching out to everybody in the email list, fill out the survey. These are all examples of convenience samples. Another interesting example is, let's say a researcher wants to study the perceptions of Chinese of American brands. One way would be to poll people in China, draw a sample from the 1.3 billion Chinese, and put the questions to them about perceptions of American brands. A more convenient option, however, would be, since most universities in America have Chinese students, why not ask them their perceptions of American brands? Yes, understandably, Chinese students are not the same as those living in China. They have demographically different, and perhaps their perceptions may have kind of evolved as they move to America for higher studies. Yet, this serves as a convenience sample, simplifying the task of gathering data. And that's convenience sampling for you. In this toy example, you can see we have 25 observations, and we have here group D might be chosen as to gather data from because it's convenient to do so. You might just pick observations 16 to 20 from 1 through 25, picking then 5 out of 25 as our sample because it's convenient to do so. In certain cases, a decision might be made to use judgment. There might be some very good reason why the researcher might believe that a sample is desirable and therefore use judgment sampling to gather data. Right? This might be the choice of test markets, for example. In America, we typically identify certain cities as being good test markets and launch products there and gather data from those places. So again, if the researcher believes there's a good reason why certain respondents are good candidates, they might use that judgment in deciding who to invite to a research study. That's judgmental sampling. In quota sampling, we try to make sure that different groups are well represented by creating quotas. So for instance, if one wants to make sure that males and females are equally represented in the sample as in the population, then they could separately draw samples or draw samples up to a certain amount to ensure there's sort of that proportion of male to female across sample and population is identical. In this particular toy example, if you have 5 groups, you could say, we want to draw one person from every group to ensure representation of every single of these 5 groups in our data. Then there is this thing called snowball sampling. Snowball sampling is often used or involves asking respondents to recruit more respondents. So imagine sending a survey out to a person and asking the person to share the survey with 2 of his or her friends. This way, the survey kind of goes like a snowball. So one person shares it with his friends, then with their friends, and so on. And what it helps to do is to get more responses. Now, cold calling a person to respond to a survey is usually doesn't have a high strike rate. On the other hand, if we ask Joe to invite his friend to complete the survey, there's a much higher likelihood the friend will complete the survey than if we reach out to that person directly. And so that's the reason why for using snowball sampling. Also, with certain groups, they may just not be accessible. It may not be possible to reach out to everybody in that group. And so snowball sampling works very well if you're, let's say, interested in gathering data from a bunch of divers, let's say, really very good deep sea divers. Deep sea divers might have other deep sea divers as friends. So if you reach out to one deep sea diver, the deep sea diver could share it with 2 of his friends and then with 2 of their friends. These deep sea divers might know other deep sea divers, right? And that's the motivation of using snowball sampling. Clearly, your friends are all like you, and therefore the sample is not guaranteed to represent the population. Therefore, yet another example of non-probability sample. Now, we've looked at non-probability samples. Now, the beauty about probability samples is that with a probability sample, each population element has a known non-zero chance of being included in the sample. Right? So we can calculate the likelihood that any given population element is included in the sample, and this in turn can enable the computation of sampling error, something we cannot do with non-probability samples. So a lot of statistics then assumes that our data is in fact a probability sample. Specifically, I'm referring to inferential statistics. Let's begin looking at the different kinds of probability samples. The most popular one is simple random sampling. This is simple, as in pretty much every software out there is able to very quickly and easily randomly select a certain number of observations. So very, very simple method. We tell the computer, randomly choose 25 observations. And one thing computers do very well is pick things at random. Another type of probability sampling is systematic sampling. This attempts to mimic random sampling by using a system to choose observational units. For example, if you have let's say a database of 1,000 observations and you want to choose, let's say, a sample of 10, you could choose every 100th observation. So the system or plan to choosing the observation, 100, 200, 300, 400, so on to 1,000 will give you 10 observations chosen by systematic sampling. If there's no good reason why somebody should be a certain ID number in the database, then systematic sampling should be fairly representative. So in this case, in our toy example, imagine taking the second observation for every group. Now, stratified sampling is typically used when one isn't sure that every strata or group will be adequately represented in the population. To illustrate the point here, now we expect randomness, random processes to work out, and they do on the long run. Like if you were flipping a coin, infinite number of times, you'd get half heads and half tails. However, if you flip a coin, a fair coin, 10 times, you could end up with 3 heads and 7 tails, or even 2 heads and 8 tails. So one wants to be sure that if a certain variable of interest, the sample is proportional to the population, then one could make strata and separately sample from individual strata. So there are 2 kinds of sampling, stratified sampling here, proportion and disproportion. Let's focus here on proportional sampling. In our toy example here, we have 5 groups. If you want to ensure that every group is equally represented, what we could do is we could say we will create our 5 strata as group A, B, C, D, E. From every group, we're going to draw exactly 1 observation randomly. This will ensure that each group is equally represented in our sample. There might be scenarios where you may feel that you want to make sure that you have an equal representation of people with high income and medium income in your data set. Therefore, you might divide the data set into the population or sampling frame into high income, medium income, low income, and then separately sample from each group so that you get a proportion of high income that mirrors the number in the population. That's stratified sampling. Now, there are cases where you might not just do proportionate stratified sampling, which is alluded to, but do disproportionate stratified sampling. This is done when you feel like certain strata are more interesting. So they're more interesting because there's more variance in them. Right? So in this case, the size of sample for each stratum is inversely proportional to the variance of each strata. If there's a lot of variation in a certain strata, you might say, let me draw more data from that strata. In the strata with less variance, let me draw less data from that strata. And that's disproportionate stratified sampling. Moving along, we have cluster sampling. In cluster sampling, we randomly pick a cluster. Imagine you want to study the uh, attitudes towards dogs for people in New York. What you could do is you could look at all the blocks. So New York City is broken down into zip codes and census tracts down to blocks. The block is the smallest unit that the US Census shares data on. So we could then take a look at all the blocks and randomly choose one block. And for the people living in that one block, we'll survey all of them and ask them their attitudes towards pets. So the choice of the cluster was random. This is an example of one-stage clustering. There's also two-stage clustering. Well, two-stage clustering occurs when we say we are going to randomly select a certain number of blocks, and then from those blocks in New York City, we're going to randomly choose a certain number of households within each of the chosen blocks. That's your two-stage cluster sampling. So in our toy example here, you can randomly choose, 3 clusters. So here B, D, and E are the chosen ones. And from those 3 clusters, we randomly choose, again, some elements from each of those 3 clusters. That's your two-stage cluster sampling. Okay, so all said and done, each one of these sampling techniques have their strengths and weaknesses. I'm going to focus here mostly on probability sampling techniques, simply because I'm a little biased. Okay, with non-probability sampling, we cannot know sampling error. With probability sampling techniques, we can. So whenever you have a chance, you want to go with a probability sampling technique as your choice. Amongst those, you've got simple random systematic stratified cluster sampling. Theoretically, simple random sampling should just work. But if you don't think it's going to work well enough, you could use stratified or cluster sampling if you feel like it might address some of the issues with simple random sampling. Systematic sampling was probably more popular to use when we didn't have the benefit of computers choosing for us a random set of observations. So moving along, let me highlight why I'm emphasizing the importance of probability samples. So it turns out that for a given population, if your sample is chosen as a probability sample, then the mean of all possible samples is equal to the population mean. So let's just imagine you've got, a population of 100 observations. You draw all possible samples, average each sample. The average of the samples will be exactly equal to the population mean. Let's think about this one more time. If you would take a population of 100 observations and you were to draw many samples, not all possible samples. As you draw more and more number of samples, the average mean of all the samples, just average every sample and average those sample means, that average will approach the population mean. Therefore, the sampling mean being the mean of all the samples, is an unbiased estimator of the population mean. Furthermore, there's a simple formula that links the variance of all the sample means to the population variance. For small samples, it's simply the population variance divided by the number of observations. By small samples, I mean samples that are smaller than 10% of the population. What we also know is that if you have a sample that is sufficiently large and you construct a distribution of all the sample means, they will approximate normal distribution. This is independent of the shape of the population. This is the well-known central limit theorem. Let's take a look at an example to better understand this concept. In this hypothetical population, we have 20 observations. and label elements A through T. We have here income, education, and we know whether they subscribe to a magazine or not. We have 3 variables of interest out here. We're going to focus here on one of the variables, income. Imagine from this population of 20 observations, you drew very small samples, sample size 2. Now, with 20 observations, you can draw at most 20 chooses 2 or 20 C2 samples. That's the maximum number of samples we'll have repeating. Which turns out to be 20 times 19 divided by 2, or 190 possible samples. So imagine we drew 190 samples, all possible, samples of 2 observations, and we compute the mean for each sample. Right? The average of all those sample means will be exactly the same as the population mean. Furthermore, if you were to examine the distribution of the sample means, you're going to find that distribution of sample means looks very normally distributed. As you can see, in our toy example, the bulk of the sample means are somewhere in the middle. And this curve looks nice and normal, or bell-shaped. Based on what we know about central limit theorem, it doesn't even matter what the population is. The sample mean, or the sampling distribution of means, or sampling distribution of sample means, will tend to be normal as n goes up. So our population here is, very strange, like distribution for the first one. And you can see here, as n is 2, you get a kind of a triangular distribution and more bell-shaped. And then as your n goes up, your distribution tends to look more and more normal, regardless of the population shape. We're seeing this with all sorts of examples. Every one of them, as n goes up, even at n30, what is not at all normal or bell-shaped in the population is fairly smooth and bell-shaped in the sample, in the sampling distribution. Okay, so what all this gives us is the following. Knowing the sample means are normally distributed enables us to state percent of sample means within a specified range of population. Example, for instance, here we have sorry, it should be we have here mu minus z sigma x smaller than equal to x bar, smaller than equal to z sigma. You can rearrange the terms to get the following, right? So the benefit of this is we can make statements now about 95% of sample means lie within lie within plus minus 1.96 times the standard error, right? So we can make all these statements because we now have, we know the sampling distribution is normal. Okay, so we can then look at, for example, a distribution like this, and now we can make statements about, okay, this area is because our sampling distribution is normal. This area is 34%, and if you were to combine this area together, that would give you 68% of the area, right? And this would be 95% and so on, 95.5%, 5% and so on. We can make all these statements because we now know the sampling distribution is normal. Okay. All right. Moving along now, I'm going to talk to you here more about again, statistics and parameters. So the population is what we're interested in knowing more about. The sample is typically what we have access to. So we are interested in knowing about certain population parameters like mu, but we only have access to sample statistics like x bar. What we end up doing is using the information about the sample statistic to infer something about the population. Hence, this world is called the world of inferential statistics. Let's examine, let's just quickly review out here the terminology. Then you can notice that if we talk about population, we use different symbols than for sample. So on. Okay, so let's move into a sample size consideration, or considerations for sample size. One of them is in figuring out how large the sample size should be. One factor is the type of sample. Do you have a probability sample or non-probability sample? That's one consideration in sample size. The second is the statistic or statistics in question. There is then a mathematical way of figuring out sample size. We can look at that in great detail. And then there's the issues of homogeneity of population. Generally speaking, there's more variation in the population. You'll need a larger sample size. The more noise, more variation there is, the larger your sample size will have to be. And the last is probably the most important consideration. We would like to have a large sample, but there are constraints on time, money, and personnel for any given study that might put a cap on how much data we can collect or gather. Let's begin by examining this little equation out here, which we've seen before. So mu equal to x bar plus or minus, excuse me, z sigma x bar. Now you can simplify this equation, rearrange the terms out here to do something like this: mu minus x bar is equal to z. We know sigma x bar is, for small samples, sigma divided by square root of n. We can approximate this to be sigma to be s. That is, we'll approximate the population standard deviation to be same as sample standard deviation here. So you end up with this equation looks like this. So mu minus x bar here is nothing but the difference between the true value mu and the sample value. That's the amount of the interval of confidence interval we're willing to kind of accept, or precision we're willing to accept out here. We'll call that D or H, doesn't matter. Let's stick with D for now. And on the left side, right side, we still have ZS divided by root N. Rearranging these terms, you can get N as being equal to Z squared S squared by D squared. Okay, let's examine what these pieces mean individually. The Z statistic out here refers to how much confidence do you want in your inferences you draw. So if you want 95% confidence, 99% confidence, the more confidence you want, the higher the Z value is going to go up. The more confidence you want in your result, the more sample size you're going to need. The second is the importance of S. The higher the sample or higher the standard deviation there is, the variation there is in the data, more noise there is in the data, the larger sample size you're going to need. And if you want your results to be more precise, you want D to be as small as possible. Right? The more precision you want, the larger sample size you're going to need. So by plugging in a numbers for Z, S, and D, you can come up with a projected sample size. Let's be more concrete out here with this example. Let's just say our goal for the level of precision here is to be D. Confidence level is 95%. Knowing the confidence level 95%, we get a Z value of 1.96. We have here 5 for D, Z is 1.96, and we're going to estimate you can get a standard deviation. You can either know the standard deviation of the population from experience, or you can estimate it from doing a pilot study of a sample. Assuming we have some estimate of standard deviation available from a prior study or just experience, it could even be a a guesstimate of the population standard deviation. Plugging in the numbers, you can get here a sample size estimate, 465 in this case. We can do a similar approach to figure out, again, sample size for proportions as well. So let's think about what this means with an illustration or example. So imagine your sample size is 5, n is 5. If the sample size is very small, the 95% confidence interval, your interval width is going to be large. As your sample size gets larger and larger, your confidence interval or your precision is going to get better and better. Better means a narrower, more precise kind of estimate of whatever you're measuring or evaluating. You can see as your sample size gets up, your precision is getting to be higher. Here's a visual, the same thing. So as your sample size goes up, your confidence bands get narrower. This range is getting more tight as your sample size goes up. Furthermore, you can try this with a 99% confidence interval. What if you want to look at even more confidence in the result? Well, you're going to find out between 95 and 99. If you want 99% confidence, your confidence bands are going to get wider. The dotted line here looks at 99%, and the solid line looks at 95%. You can see here, as you go from 95 to 99, you want more confidence, then your confidence interval is going to grow, precision will drop. So you can see how all these different things are interconnected. Okay, so to sum up here, the equation makes it look really easy, like you can just plug in a few numbers and figure out, again, what is the projected sample size for the study at hand. But let me go back to point number 2 out here, the statistic in question. In the example we had up there, we're looking at one statistic, using that to drive our decision of, based on how much precision we want for that standard deviation there is, and so on, we're figuring out sample size. What if our study involves many different variables? Well, then you got to look at every single variable to figure out, based on that, what is the minimum sample you need to satisfy each variable. And I cannot emphasize enough the importance of time, money, and personnel in defining or deciding on sample size. Okay, to wrap up then, in this section, we have contrasted sample and census, examined the sampling design process, explored various probability and non-probability sampling techniques, examined the weaknesses and strengths of these sampling techniques, and lastly, determined sample size using mathematical considerations as well as some qualitative considerations. Thank you.